All right, so we're in 4.3 now, and in the previous two sections of Chapter 4, we've been exploring historic numeration systems. We've looked at Egyptian, ancient Roman, Mayan, and what was the other one? I'm blanking on the other one all of a sudden. Babylonian, that's what it was. Yeah, so four historic numeration systems. And we have mentioned here and there the Hindu-Arabic system, which is the numeration system that we currently use. It's a base 10 positional numeration system, and we've already talked about what that means. So what we're going to be doing here, 4.3 and 4.4 as well, is kind of digging a little deeper into this system, looking at how we do arithmetic in Hindu-Arabic and why the arithmetic that we do or the why the methods that we use for adding and subtracting and multiplying and so on in Hindu-Arabic work the way that they do. So the first place that we want to start is thinking about place value, which we've already talked about. So take as an example the number 2,493. Each digit, as we know, has both a face value and a place value, and the place value determines which power of 10 that digit represents. So 2,493 represents 2 thousands, 4 hundreds, 9 tens, and 3 ones, or we also call the ones place the units. Taking this phrase here, 2 thousands, 4 hundreds, 9 tens, and 3 ones, and trying to represent that mathematically, 2 thousands is literally the same thing as 2 times 1,000, and 4 hundreds is the same thing as 4 times 100, 9 tens is 9 times 10, 3 ones is 3 times 1. So we can take that number and write it out in this longer form that gives a little bit more insight into what each place value represents. But beyond that, the place values represented here, the 1,000, 110, 1, those are all powers of 10. So really, I can rewrite each of these as 10 to some exponent. For example, 1,000 is 10 cubed, 100 is 10 squared, 10 is 10 to the first power, and 1 is 10 to the power of 0. This is an important one to remember. In algebra, any number to the power of 0, with the exception of 0 to the power of 0, which is undefined, but any other number, any non-zero number to the power of 0, is always equal to 1. So you can see these powers of 10 where the exponents are kind of descending as you go from left to right. When we take a numeral or a number in Hindu-Arabic form and we write it out in this long form like this, where we have the digits multiplied by the place value represented as 10 to a power, and then we sum all of those. This is called the expanded form of this number. So my first example, I want to look at writing a different number in expanded form. So 3,091,402. We want to write that in expanded form. And the trick is just to remember which place value is represented by each digit. And then to not just think of that place value as you would read it, but think of what power of 10 it's equal to. So for example, this 3 here is in the millions place. But rather than write 3 times 1 million, I'm going to recognize that 1 million is the same thing as 10 to the power of 6, and write this as 3 times 10 to the power of 6. So here's my representation of the 3 million appearing here. Now, I have a 0 in my 100,000s place. 100,000 is 10 to the power of 5. And even though 0, if I write that out using this expanded notation, 0 times 10 to the 5th, even though that's technically equal to 0, which means that adding this is like adding 0, and I can technically just not even write it without changing anything, I'm still going to write 0 times 10 to the 5th so that I have a representation for that digit somewhere. Continuing onward, my next digit is 9, and we expect the power of my 10 to keep decreasing by 1 each time. So 9 times 10 to the 4th, plus my next digit is 1, 1 times 10 cubed, plus 4 in the hundreds place would say it would be 4 times 100 or 4 times 10 squared, plus we have another 0, but we still write it, 0 times 10 to the first power, plus 2, my last digit, times 10 to the power of 0. Just barely squeezed that in there. Okay, so that's the expanded form for that 7-digit number. And yes, it's a very cumbersome way to write that, but the idea is not to make things simpler, it's to give insight into what each of these digits represent. Okay, let's see about doing this in reverse order. I'd like to simplify this expansion, and as we've seen, the number that's being multiplied to each power of 10 really just represents a digit in that numeral. So I'm going to focus on these digits, 4, 9, 0, 1, 8, 1, and I do want to make sure that all of my powers of 10, starting from the largest on down to 10 to the power of 0, are represented here. So I have 10 to the 5th, 10 to the 4th, 10 cubed, 10 squared, 10 to the 1st, 10 to the 0. I have everything, and it's all in the correct order. So let's write those digits out. 4, 9, 0, 1, 8, 1. Put a comma in there. That's 490,181. So obviously going this direction is a lot quicker than going that direction, where we had to expand. But it's good to be able to go both directions. Now, the idea in this section is to look at doing arithmetic in Hindu-Arabic form, specifically how arithmetic works when we take a numeral like this one and put it in expanded form. And a big tool that's going to be used here, without explicitly thinking about it as being used, is the distributive property. So remember, the distributive property says that if you have a number being multiplied to a sum, and that sum is in parentheses, you can distribute the number being multiplied into the sum. And where we're going to be using that is when we have numbers that look like parts of these terms in expanded form that have 10 to the same power. So for example, if I wanted to add 4 times 10 cubed plus 4 times 10 cubed, both of these are 10 cubed. The distributive property is what justifies factoring things out. So if I factored this 10 cubed out and left the 4 plus 5 in parentheses, then this is 4 plus 5 times 10 cubed. But then the parentheses here would suggest that I need to add 4 plus 5 first before multiplying by 10 cubed. 4 plus 5 is 9, and so I get 9 times 10 cubed. So basically what this says, and what the distributive property is allowing us to do, is to take numbers written in this form, 4 times 10 cubed plus 5 times 10 cubed, and simply just add these two single-digit numbers. 4 plus 5 is 9, and then keep that 10 to the power the same as what it was, 10 cubed, 10 cubed, 10 cubed. Okay? So we do this without thinking about it. We add the 4 and the 5 without really going through the process of figuring out why that's justified, but the distributive property is what's justifying the arithmetic that we do here. Okay. So let's start by doing some arithmetic. We're going to do addition and subtraction using the expanded form of these numbers. So I would like to add 41 plus 76. Now I know you know how to do this by hand, no problem, but what the idea here is to show why the technique that we use for addition works the way that it does. So if I were to just write 41 plus 76, the way you would normally think to do that is to add vertically. 1 plus 6 is 7. I would write a 7 here. 4 plus 7 is 11. I would write an 11 there. And then that would say 117. So that's easy, right? But again, oftentimes we get so used to the algorithm for performing a computation like this, we stop thinking about why we're doing that in the first place, why that works. And here's where we're going to justify that. So if I rewrite this addition problem by taking each number that's being added, we call those addends, and write them in expanded form. I have 4 tens and 1 1, which I can write as 4 times 10 to the first power plus 1 times 10 to the power of 0. Okay, and to that I'm going to add 76, which has 7 tens, 7 times 10 to the power of 1, and 6 units, or 6 ones, 6 times 10 to the power of 0. Okay? Now technically all of this is being added into one number to get a single sum out of all of this, But because I'm adding all 4 of these terms, in light of that distributive property that we talked about, it makes sense to focus on adding numbers that have the same power of 10 in them, because that's where we're justified in just adding these single-digit numbers using that distributive property. Well, vertically, I've aligned these things so that powers of 10 that match are on top of each other. They're stacked up. So if I try to add 1 times 10 to the power of 0 plus 6 times 10 to the power of 0, that distributive property says that we just need to add 1 plus 6, which is 7, and then I keep my power of 10 the same as it was. So now I have 7 times 10 to the power of 0. Okay, let's do the same thing. Whoops. Let's do the same thing here. I have matching powers of 10, 10 to the power of 1, 10 to the power of 1. So I'm going to add my single-digit numbers here. 4 plus 7 is 11. 11 times 10 to the first power. Now, whoops, a little smudgy there. This is correct, but there's an issue with it. This is not the correct way to write the expanded form of a number. And the reason for that is because whatever number we're multiplying by a power of 10 has to be a single-digit number. We can't have a 2-digit number here. So off to the side, I want to show you something that's going to allow us to break this up a little bit. 11 is the same thing as 10 plus 1. So I'm going to take 11 times 10 to the power of 1, and I guess technically I don't need the parentheses for this part, and I'm going to rewrite 11 as 10 plus 1 times 10 to the power of 1. Okay? The next thing I'm going to do is use that distributive property again to take my 10 to the power of 1 and distribute it to each term here. Now, what is 10 times 10 to the power of 1? Well, this is 10 to the power of 1 as well, technically, times 10 to the power of 1. I add those exponents together, and that gives me 10 to the power of 2. Okay? 10 to the power of 1 times 10 to the power of 1 is 10 to the power of 2. And here I'm multiplying 1 times 10 to the power of 1. So that becomes plus 1 times 10 to the first power. Now, technically, even though this just says 10 squared, I could also write it as 1 times 10 squared because that's still equal to 10 squared. And here I have plus 1 times 10 to the power of 1. And the point of doing this is that it allows me to take this term right here and break it up into something that's technically the standard form of a number. So if I were to write 11 times 10 to the 1 this way, I now have 1 times 10 squared plus 1 times 10 to the power of 1 plus this guy right here, 7 times 10 to the power of 0. Now this is the standard form for the number 117. And remember, that's what we said our answer should be, 117. Again, I want to emphasize something. Looking at this, you might be shaking your head thinking, why on earth would I go through all of this trouble to add a number that it took me 5 seconds to do by ignoring all this and just adding 1 plus 6 to get 7, 4 plus 7 to get 11. Like less than 5 seconds and I'm done. Why would I care to do all this? And it's really important to recognize that this is not intended to be a more efficient method. It has nothing to do with being a good algorithm for computing, addition problems. The idea is to actually show why this technique works in the first place. It's to give justification for the way that we normally do addition. So don't confuse this with a technique that I'm saying is better than the way that you currently do it. It's actually the same technique, but it's showing you all of the machinery that's going on underneath that algorithm that you're used to. Now, this is kind of an important theme in math. We kind of get used to a lot of basic calculations, and we stop thinking about why things work the way that they do. We just focus on how they work, or how to perform those computations and whatever. And that, even though it's good to be able to do computations quickly if needed, it's overall bad to stop the critical thinking process. It's not a good thing to forget or to stop thinking about why things work the way that they do. But enough on that little rant. Let's keep going. I'm going to do the same thing. I'm going to use expanded notation to add 43 plus 24. And now what I'm going to do, when I come across something like this, where I have a 2-digit number times the power of 10, I'm going to go from this straight to this without doing all of this work on the side. Now that you've seen it once, we can kind of see, what's going on there. But here, let's add these two numbers, 43 plus 24. So it's just another example to kind of get us practicing this. 43 plus 24. So if I were to write these in expanded form, 43 is 4 times 10 to the power of 1 plus 3 times 10 to the power of 0. And then 24 has two tens, so that's 2 times 10 to the first power plus 4 times 10 to the power of 0. And again, we add everything vertically. Without thinking about the distributive property, we're still using it to justify adding the 3 and the 4 here. That would be 7. Matching powers here says that this would be 10 to the power of 0. Similarly, 4 plus 2 is 6. And I get 10 to the power of 1. This time I don't have a 2-digit number here, and so I know that the answer is just 67 from the 6 and the 7. What was happening here when you're splitting up this number into these two parts, this is what carrying a 1 is in adding numbers. This is what it looks like when you're working in expanded form. Here we didn't need to carry any 1s if we were adding these, and so no terms had to be split up the way that we did previously. Okay, I think I meant to make this one a subtraction problem. Let me see something here. Oh no. Okay. So I think actually this problem right here. Oh no. I do want to do this one. Sorry, I was thinking I had too many here. Let's do one more where we do 56 plus 38. 56 plus 38. So another addition problem. I can write this as 5 times 10 to the first power plus 6 times 10 to the power of 0. That's 56 in expanded form. Plus 3 times 10 to the first power plus 8 times 10 to the power of 0. So this is another case where we have carrying to do, but it's not going to look like carrying. Because if I were to add these, 6 plus 8, that's 14. 14 times 10 to the power of 0. And we see a problem here, right? We see that we have a 2-digit number where we really should have a single-digit number. So we'll deal with that in a minute. Let's add these. 5 plus 3 is 8, so this gives me 8 times 10 to the power of 1. Okay, now normally over here, if I did 6 plus 8 and got 14, I would just write 4 and then carry a 1. But we want to think about why that's happening using expanded notation. So I have my 8 times 10 to the power of 1. I don't see an issue with that because there's a single-digit number here like we want. This guy, though, I need to expand that out. And again, remember, I can take 14 and write it as 10 plus 4. And then distribute the 10 to the power of 0 into that sum. Same idea as what we did up here. What would that make this look like? Well, the 10 here would be multiplied to this 10 to the power of 0, and 10 to the power of 1 times 10 to the power of 0 is 10 to the power of 1. So this gives me plus 1 times 10 to the power of 1. And then the 4 that remains is what's left in my units. So 4 plus 10 to the power of 0. So basically, this 14 times 10 to the power of 0 got split up this way, okay? Now, if you look at what happens, I have like terms here. I have 10 to the power of 1 and 10 to the power of 1. So using that distributive property again, I can add these together by just doing 8 plus 1, which is 9 times 10 to the power of 1, plus 4 times 10 to the power of 0. And as you would have found if you had just added these directly the way you're used to doing it, we end up with 94 as an answer. Okay, so this is what carrying, again, looks like when doing things in expanded form. In fact, the term that we often use for carrying is regrouping, and that's exactly what's happening here. We're taking this term, expanding it into a sum of two terms, and then regrouping one of those terms with this guy over here, making it 9 times 10 to the power of 1. Okay? Let's try looking at subtraction in expanded form. So here I have 459 minus 221. 459 minus 221. We want to write this in expanded form. Now I have 3-digit numbers, so these are numbers that are in the hundreds place, and 100 is 10 squared. So in expanded form, we have 4 times 10 squared plus 5 times 10 to the first power plus 9 times 10 to the power of 0. Don't forget the last power of 10 is 10 to the power of 0, not 10 to the power of 1. And then I have 2 times 10, oh, this is subtraction, sorry, subtraction. 10 squared plus 5 times 10, oh, sorry, 2 times 10 to the first power plus 1 times 10 to the power of 0. Rushing that a little bit, that should be a 2. Regrouping here, sorry, not regrouping, but subtraction in expanded form is going to work in much the same way as addition, where we're using a distributive property. Now, one thing that's actually important here is that we're subtracting this entire number. But the way that I've written this, it looks like we're only subtracting this part, and then I'm adding these parts, and that's not correct. I should actually put these in parentheses to show that I'm subtracting all of this, which is 221. That means all of these pluses would technically change to minuses, which just means I'm subtracting instead of adding vertically. So I have matching powers of 10. 9 minus 1 would be 8 times 10 to the power of 0. 5 minus 2 would be 3 times 10 to the power of 1. 4 minus 2 would be 2 times 10 to the power of 2. Okay, so this is what I end up with in expanded form. That's 238. Okay, that one wasn't so bad because the subtraction all worked out really nicely. But one thing that you do know from subtraction, having done this plenty of times, I'm sure, in the past, is that sometimes you have to do borrowing. So I want to look at a case where that happens. And then we'll do this last example for this video, and then start the next video down here. So I want to do 52 minus 37. 52 minus 37. Let's put this in expanded form. I have 5 times 10 to the power of 1 plus 2 times 10 to the power of 0 minus, remember these little brackets here are necessary, 3 times 10 to the power of 1 plus 7 times 10 to the power of 0. Okay, and here we run into a problem because I'm trying to do 2 minus 7. Now I know that I could technically call that -5, but remember, you are supposed to learn how to do subtraction long before, like subtraction of this type, long before you're ever introduced to negatives. So we shouldn't have to rely on negatives to do something like this. Instead, we're going to try regrouping, and this is going to look like borrowing in reverse. So what I'm going to do is take one of the 10s here. Notice I could write 5 times 10 to the first power as 4 times 10 to the first power plus 1 times 10 to the first power. And then I have the rest of this problem, 2 times 10 to the power of 0. Okay, everything else is going to look the same. 3 times 10 to the power of 1 plus 7 times 10 to the power of 0. Now, what am I trying to do here? Well, what is 1 times 10 to the power of 1? It's just 10, right? 1 times 10 is 10. So I have 10 here, which can either be thought of as 110 or 10 ones. If I think of it as 10 ones, then I can use that to combine with this number over here, which is a ones place digit, 2 times 10 to the 0, which is 2 times 1. So in other words, I have 10 ones here, and I have 2 ones here. Cumulatively, I have 12 ones between these two terms right here. So that means I could rewrite this as 4 times 10 to the power of 1 plus 12 times 10 to the power of 0. Then I still have 3 times 10 to the first plus 7 times 10 to the power of 0 here. Okay, now even though technically this is not the correct way to write a number in expanded form because we have a 2-digit number here, its purpose is to help me do this subtraction. See, previously this digit was just a 2, which is too small to subtract 7 from. But now it's big enough to subtract 7 from. And when I do that, I didn't really leave myself a whole lot of space here, I can do 4 minus 3, which is 1 times 10 to the power of 1, plus 12 minus 7, which is 5 times 10 to the power of 0. And that's equal to 15. Okay, so this is what borrowing looks like in expanded form. And again, just to emphasize, this is not meant to make subtraction easier. Obviously, it makes it much more complicated, but that's not the point. The point is to see what's going on beneath the surface when you're doing this borrowing technique that you've internalized and gotten used to. Okay, starting in the next section, we'll start looking at some historic ways of doing addition and multiplication. So that's going to be part 2.